finally non-quantum classical probability theory, and it's about what the title indicates. The general properties of Bayesian learning based on conditional expectations, conditional device. It's joint work with Zolán János, a young mathematician, logician in the Technical University, Budapest University as well. So, what's the page now?
Oh, the final left arrows?
It's just slow.
Okay, I hope I will be able to navigate. Okay, so what's the main message? I'd like to summarize the main message of the first slide. The first part of the main message is that Bayesian learning is nothing but a statistical inference. Namely, you infer probabilities from other probabilities, which are called evidence, and you do this via conditionalization as the inference device. That's the first claim. I would like to portray Bayesian learning in this way. The second part of the message is that the standard way of conditionalizing in general is based on the theory of what is called conditional expectation. In mathematics, this is standard. This is how you should conditionalize in general. And the standard Bayes rule and what is known as Jeffrey conditionalization, which are special cases of conditionalization by conditional expectations. But if you want to talk about Bayesian learning in general, you have to use the technique of conditional expectations to conditionalize. So that's the second part of the message. And if you do this, if you approach Bayesian learning in this way, then basic fundamental features of Bayesian learning become visible, more visible perhaps than otherwise they would be visible. And in particular, I'm going to discuss two features, two phenomena in connection with basic structural features of Bayesian learning. One is the existence and implies properties of Bayes blind spots, what we call Bayes blind spots. And the other is the existence or non-existence of royal rule in Bayesian learning. And my plan is just to describe, make it clear what this means. That's the Bayesian learning is based, of course, on probability theory. And throughout the talk, I will take a standard classical probability measure space with S being the Boolean algebra. It's assumed to be a sigma field, but I'm suppressing all the technicalities here. And the probability measure, which I take to be the background knowledge of a Bayesian agent. So Bayesian agent and a classical probability measure space are synonyms for the purpose of this talk. The simplest Bayesian learning situation or inference situation which a Bayesian agent can find himself is the following. Suppose you ask the Bayesian agent, what probability values QB being S would he infer from the information that for a fixed A, the probabilities are given by these numbers. 1 on A and 0 on non-A. And since we are talking about the Bayesian agent, of course he has a ready answer to that. I'm a Bayesian agent, so I would infer these probabilities here, which is just the Bayes rule, written in a somewhat explicit form for the purposes of the next slide. And I would like to read this Bayes rule in the following way. The agent has inferred from Q, from the evidence, which is the value of it on A being equal to 1, and the value of it being equal to 0 in its component, on the basis of his background, which is P. Okay? That's what the Bayes rules reading in Bayesian learning, in Bayesian statistical inference means. The next situation is slightly more tricky. You can ask the Bayesian agent, what probability values QB on B would you infer from the information that for a fixed A now the probabilities are not equal to these extreme values, 1 and 0, but some other real number here. Okay? Not 0, not 1. The Bayesian agent, of course, not bothered. It's a Bayesian agent. He can give an answer based on the same pattern of inference. Remember, that was the previous pattern on the slides too. In this case, now these numbers are not 0 and 1, so the inferred values will not be given by the Bayes rule, but it's Bayesian nevertheless, in this very elementary sense. Again, what the agent has done here is that he has inferred Q from what is called the uncertain evidence in the literature of Bayesianism, namely the values of Q in a particular subalgebra, actually, which is generated by A and not A, on the basis of his background measure. Now, this Bayesian statistical inference, formulated in the previous slide, defines a two-place relation which I call the elementary Bayes accessibility relation, a two-place relation that is in the set of all probability measures on that Boolean algebra. Namely, this relation, Q prime is related to Q if there's a Boolean subalgebra generated by one element, such that QB can be obtained from Q prime in this way. And the interpretation of this Bayes accessibility relation is that the Bayesian agent, represented by the probability measure, can learn Q from this evidence, which is the value of a measure on this particular subalgebra, which is very elementary. It's the smallest non-trivial algebra. And he can do that by Bayesian conditionalization using his background probability. There's nothing new going on here. This is all well known. But then we can push the Bayesian agent a bit more. Suppose we ask him, what probability values will you infer from the information that you are given the probabilities on a partition? Possibly an infinite partition, a countably infinite partition. Well, the Bayesian agent, again, has an answer to that. Namely, he can use, again, the same pattern. This is the same pattern as you see. It's just in a compact form. And this is also very well known, what this pattern is. That's the Jeffrey rule. So what the agent has done in this case is that he has inferred Q from the uncertain evidence, which in this case now are the values of the probabilities on a whole, possibly countably infinite partition, by which he also is given the by which also a probability measure is given on the algebra, sub-Boolean algebra, which this possibly countably infinite partition defines. And then using this inference pattern, the Bayesian agent can define, or we can define rather, what I call here the Jeffrey accessibility relation, which is really the more general form of the elementary Bayes accessibility relation. Namely, one can say that Q prime and Q stand in this Bayes accessibility relation if there is a Boolean subalgebra generated by a possibly infinite partition, countable infinite partition, such that this Q can be obtained from this Q prime using the Jeffrey rule. Okay. And the interpretation is again the same. The Bayesian agent can learn Q from the evidence, from this uncertain evidence, which is the values of the probability and partition by Jeffrey conditionalization. Now we can also ask the question then, and I'm sure you anticipate what the next question is. Suppose the Bayesian agent is asked what probability values he will infer on B from the information that the probabilities are given on an arbitrary Boolean subalgebra, necessarily generated by a partition, by a countable partition. Well, the Jeffrey rule doesn't have here. So what does the agent do? The agent might pose a little bit. The question really here is there a rule that allows the agent to infer a probability measure from some general uncertain evidence? And the answer to that question is yes. I'm not the chair. But it might be.
Let's wait till discussion, please.
So there is such a general inference rule, and that general inference rule is given by the notion of AP conditional expectation. You're given a background, you're given a subalgebra, and there is then a rule which is based on the notion of AP conditional expectation, which gives you an answer to this question. Okay? This is how the general Bayesian learning emerges from this pattern. If you use the notion of conditional expectation with respect to an arbitrary subfield and given a prior, then you get an upgrading rule, an inference rule, as I would put it, that would be such that it allows you to give an answer to this question, what the probabilities are on arbitrary elements once you have given a subalgebra on which you're given a probability measure which serves as your evidence. Some comments on this conditional expectation. This notion was introduced into probability theory by Kolmogorov in 1933 in his famous book. Jeffrey introduced his Jeffrey rule, in 1965 in his book. And he says there, which I'm quoting, to discuss the matter more rigorously and generally, it is necessary to use the notion of integration over abstract spaces. But as far as I know, he did not work this out in detail, nor did he refer to the theory of conditional expectation. Well, this is worked out in great detail by Kolmogorov. In fact, he doesn't even refer to Kolmogorov in this book, which I find a bit surprising. On the other hand, if you read standard, bit more advanced textbooks on probability theory, where the notion of conditional expectation is described in detail, they don't refer to Jeffrey. So this is a bit puzzling to me. I don't quite understand why these two developments have been so unrelated. Why is it that the conditionalization along the Jeffrey lines did not take notice of the conditional expectation concept, where this notion has been around for a very long time. Here is the definition of the conditional expectation, but I don't want to detail it. This is the technical exposition, technical definition of the conditional expectation. I'm flashing this just for the visual illusion, not for the intellectual impact, so I'm moving on. Saying that with this notion of conditional expectation, again, you can design this two-place relation in the state space, in the space, in the set of all probability measures, by saying that these two measures stand in that relation, if it's true that there's a Boolean subalgebra, an arbitrary one, such that Q can be obtained from Q prime by conditionalizing using this AP conditional expectation. It's the same relation as the Jeffrey and the elementary base, except that now the Boolean algebra can be arbitrary. It is strictly speaking true that this is the relation of these relations. These are strictly speaking special cases of the general concept of conditional expectation. And again, the interpretation of this general Bayes accessibility relation is that the Bayesian agent can learn Q from evidence, which is the probability measure on a subalgebra A. And if this subalgebra is proper and non-trivial, I would say that the Bayesian agent can learn that Q non-trivially if the two measures are in this relation. So then what this boils down is that if you want to characterize general Bayesian learning, you have to characterize this relation, this abstract general Bayes accessibility relation, which is based on the theory of conditional expectations. This is what I'm going to do here. The first proposition, which is not even a proposition, it's an observation rather. It is that if Q and Q prime are in this relation, that is to say, if the agent can infer Q from Q prime from some with respect to some algebra, then it holds that if the prior probability, the background probability of B is equal to 0, then all these two probabilities have to be 0. This is a well-known phenomenon already in elementary Bayes conditioning. The way I'm going to express this is that the general Bayesian learning takes place in the set of probability measures that are absolutely continuous with respect to the background measure of the agent. This is what the absolute continuity definition is. And I call that set of probability measures the P state space. A set of all probabilities which are absolutely continuous with respect to the background measure. Bayesian learning can take place on the basis of that background only in that set. The next proposition is also quite trivial, but it's reassuring. This relation is reflexive. As you would expect it to be, any probability measure can be learned trivially in Bayesian from itself. If this were not true, I think the relation would not be a really good relation, but this is reassuring. The first non-trivial proposition here is that this relation is antisymmetric. This means that if you can learn Q prime from evidence Q, and you can Q from Q prime as evidence, then the two must be equal. So what this means is that the state space is not strongly Bayes connected. It's not true that any probability can be learned from any other. This is just not true. In other words, this Bayesian learning is a directed something. What can be Bayes learned from some evidence cannot serve as evidence to Bayes learn the evidence itself. So this Bayesian learning introduces a direction. It's a directed something in this sense. If you have been able to learn something from some evidence, then what you have learned cannot serve as evidence to Bayes learn that evidence itself. It's not possible unless the two are the same. This is not, I think this is a, I'm not sure if this is a good feature. For the rest of this, I'm not assessing the features of Bayesian learning from some epistemological point of view. I just would like to display what features that thing has. And one of the features is this directedness. It's up for the Bayesians to judge whether this is a good thing or not a good thing, but certainly this is what happened. Now, if this state space is not strongly Bayes connected, then I'm sure you already anticipate the next question about the connectedness features, namely whether it's weakly Bayes connected. That is to say, is it true that for every probability in the state space, there is another probability different from it, such that that probability is Bayes accessible from that other? That is to say, you can learn it from the evidence. Weak Bayes connectedness, I think, is a sign of strength of Bayesian learning. In what sense? Well, if a state space is Bayes connected, then for every probability measure in that state space, there is an other from which you can learn it in a non-trivial manner via Bayesian statistical inference, which means conditionalizing. On the other hand, if Bayes connectedness, in the weak sense, is not a feature of that state space, I think that sets a strong limit to Bayesian learning in that context. Because that would mean that given the background measure of the Bayesian agent, there exists probability measures absolutely continuous with respect to the background, for which there is no evidence on the basis of which the Bayesian agent can learn it via conditionalization. So our state space is weakly Bayes connected. we must have had the abstract, so what I'm going to say here it's not going to be surprising. But what I would like to point out is that there is no general answer to this question, and it is highly non-trivial to decide. If you just give a probability measure space, and then you ask whether the state space in the way I defined it is a bit base connected, it's not an obvious thing to decide. And there are some open questions here. There will be a number of open questions which I'm unable to answer, which I'm already anticipating, and there are, I'm sure, questions which I'm unable to anticipate and I won't be able to answer either. But to indicate the non-triviality, let's have a look at this example. This is a trivial example. Consider the sixth element, the probability space which has 6 atoms. This can be used to describe results of die throwing. Okay? So suppose this is this probability measure here describes the result of the frequency distribution of die, of throwing with that die. And suppose this is the background measure. Okay? This is what I could take my private probability, or the agent takes it as a private probability. Can then this probability measure be learned from some evidence on the basis of this prior? Is there a probability measure defined on some proper non-trivial sub-Boolean algebra of the 6th element of the Boolean algebra generated by 6 atoms? There's nothing particular about these numbers. I think they are not very tricky. They are very nice looking numbers here. I think nothing strange about them. And of course, you can answer this question with brute force. What you can do is to consider each and every partition, non-trivial partition, assume as a variable probabilities on the elements of the partition, write down the Jeffrey rule for each element of this 36th element of Boolean algebra, and see, you obtain then a set of equations, and you would have to check whether that set of equations has a solution. There are 236 non-trivial partitions of this Boolean algebra. So if you do this for 236 times, 230 something times, that's the 6th real number, you would be able to solve this problem. But you can see that as the number of the atoms in the Boolean algebra increase, this becomes intractable. This is a decision problem which is not tractable by brute force. You're very welcome to check the 236 equations, but you better not spend your time with it. The answer is no.
Can I ask clarification?
Yes.
I'm not understanding something here, because isn't what you just want is to do it by brute force? You just get the information that gives you the Q values for each of the atoms, and then Jeffrey conditionalization.
But that's the trivial thing, which is excluded. What I'm asking is there a non-trivial measure from which you can infer this? That is to say, if you are given non-Q, but Q on some non-trivial sub-Boolean algebra of this.
By non-trivial, you mean not the atoms?
Not the atoms, yes. You just.
The atoms are
you don't give me each and every number here.
Right.
You just give the numbers on some non-trivial Boolean algebra. Then the question is whether from that information you can get via Jeffrey rule this measure, if this is your plan. And the answer is no. And again, these are not tricky numbers, tricky in the sense that they're, of course, done in such a way that the answer would be no. But they're not tricky in the sense that I'm not assuming that the background measure consists of, I don't know, transcendental numbers or some very weird stuff.
Sorry, can I ask another question? So when you say can it be learned from some evidence, you mean in just a single step?
Yes.
Because you mentioned that this puts a directed path over all probabilities.
This is coming.
Okay.
that changes the picture, of course. You in a good manner anticipate what's coming. But in a single set, it's not doable. Okay? Here is a general proposition about which spaces are known to have probability state spaces which are not deeply connected. A standard probability space is such that the P state space is not deeply disconnected. Standard probabilities, the notion of standard probability space is a technical notion. I'm not giving the explicit definition. I'm giving you the typical examples of standard probability spaces. They include essentially everything which one meets in applications. So probability spaces with a finite Boolean algebra are standard. Probability spaces in which this set of elementary events is countably infinite, they are standard. And probability spaces on R to the n, including n equals 1, where the probability is given with a density, biodensity with respect to the Lundberg measure, are standard. These are the standard examples of standard probability spaces. So essentially everything which you meet in applications will be such that there you have a non-deeply connected base space. And that leads to the definition of the base P blind spot. If you're given a Bayesian agent, then the base P blind spot is the set of probability measures on S that are absolutely continuous with respect to P. So there is no trivial obstacle to obtain that as a result of conditionalization, but they are not base accessible from any other measure in that state space. So again, the base blind spot of such a probability measure space is the set of probability measures in S that are absolutely continuous with respect to P, and they are not base accessible from any other measure. So in this terminology, the previous proposition can be reformulated as saying that the base blind spot of standard probability spaces is a non-empty set. So in all standard applications, there exists probability measures which the agent cannot obtain as a result of that conditionalization with respect to his background, no matter what evidence he is presented. Naturally, this leads to the question of how large is that base blind spot? Because if there is one, you might not be bothered that much. And this is a difficult and non-trivial question. Again, we don't really know the general answer to this question, and there are a number of open problems in connection with this. Part of the difficulty is that when we are talking about the size of a set, then there's no unique way of measuring it. When you're asking how large is the set, you can ask about the size in three different senses. One is the obvious, namely, it is the cardinality of it. How large is it? And in particular, how large is the cardinality of the base blind spot in comparison with the cardinality of the set of all probabilities? Because if it happens, for instance, that the base blind spot has the same cardinality as the set of all probabilities in which it is sitting, then we would clearly say that it's a very large set from the perspective of cardinality. It's as large from the perspective of size as the set of all probability measures. You can also ask the question in topological sense. There is a topological size of sets. If there is a topology in a set, there are two types of sets, meager and fat. Their first category is the meager, and the non-meager is the bare second category. I don't want to define this explicitly, these concepts in topology. I will just indicate later on an example, how the meager and non-meager sets are related to each other. That's the second measure. And certainly, if it turns out that the base blind spot is a non-meager set, then it is really very fat in the topological sense. And finally, you can ask about the measure theoretical size of the base blind spot. And in particular, what is its size in a particular measure compared to the size of the set of all the measures in the problem in this case. And if it happens to have the same size, then it's really very large, theoretically. So what's the situation here? The proposition here is that if the Boolean algebra is finite, then the base blind spot is very large. I mean, as large as it can just possibly be with respect to these three measures. It has the same cardinality, namely the continuum, as the cardinality of the set of all probability measures. It is their second category because it is open and dense in a topology, which is a very natural topology on the set of all probability measures. And it has the same measure with respect to the natural measure on the set of all probability measures as the measure of that whole set. In other words, the complement of the base blind spot, the set of base accessible measures, is measure 0. So put it provocatively, essentially, in one learning book you can't learn anything. I mean, measure 0 is not nothing. It's measure 0. It can be a large, it's not a sense, but you can't learn a lot in the sense of measure in that sense. Okay? Now, again, so one has to say a bit about in what topology we are talking about open and dense here. In the set of all probability measures, one can define matrices, distances, and the standard way of giving topology is in terms of these distances. In the set of all probability measures, there are a lot of distances. Fortunately, in this finite case, they all define the same topology. Okay? On the next slide, again, just for visual impression, not intellectual impression, I'm listing a couple of these measures just to show what they are. And it is with respect to the topology which these measures define. Is it true? It is true that it is an open and dense set, which in particular means that it's their second category, and tells that it's their second category. These are the measures: Chebyshev total variation, L1 measure, and weak star topology. But I'm jumping. There are more, and they all define the same topology. I'd like to illustrate this fatness of the open and dense set on the elementary canonical example. So the set of base accessible probabilities, the ones which can be learned on the basis of a given other, sit in the set of all probability measures like a finite set of points sits in an interval. So imagine an interval and a finite number of points. It's quite small. And that's how the base accessible measures sit in the set of all probability measures. The base blind spot sits in the set of all probability measures on the other, like the complement of an interval of a finite set of points. So if you color, say, the interval, part of the interval black, which are part of the base blind spot, then all you will see is a black. This also entails that the base inaccessible probability measure cannot be approximated with arbitrary precision by base accessible ones. Clearly, imagine the points in the interval. It's not doable. And there exists an uncountably infinite number of base inaccessible probability measures arbitrarily close to any base accessible ones. Pick up base accessible ones, there will be uncountably many around them. Arbitrary close. On the other hand, every base inaccessible probability measure has a neighborhood in which only inaccessibles are sitting. This indicates how fat topologically that set is. So this is for finite Boolean algebras. How about non-finite ones? As I indicated, this is a difficult question. We don't know the answer. What we know is that if you take a standard probability space, then the set of base inaccessible ones, the least-blind spot, is uncountably infinite. That much is known. But what is its topological size? I don't know. And what is its measured theoretical size? I also don't know. And part of the difficulty of the infinite case is that the topologies can be, there are many inequivalent topologies there. Let's not overstate. There are inequivalent ones. I don't know how many really, but there are inequivalent ones. And it's probably, but it would be an interesting thing to know whether the base-blind spot has the same topological size with respect to all or none. But again, I know nothing about this issue here. Also with respect to the measure. I have no idea. Okay, here we come to Jason's idea. The natural question then is, if in a single inference move I cannot learn a lot, and I've indicated how little I can learn in a single inference move, the Bayesian agent might consider repeat learning, a sequence of learning steps. What's the situation there? This is, to a large extent, is work in progress. We're just writing down stuff on this, but there are some observations which I can share with you here. What is important to realize is that this learning process, repeat learning, can be defined in different ways, which seem to be quite different in their behavior. One is which I call conservative Bayes dynamics, a conservative Bayesian learning process. It is characterized by the feature that you don't discard your prior, you don't discard your background, you keep yourself as a Bayesian agent. Okay? So what you do is that you look for further evidence to see which of the inferred probabilities are okay, which are not, and you keep your background probability, and you conditionalize again with respect to another sub-Boolean algebra, which means that also you discard some of the inferred probabilities and some of the evidences you had available at the first move. That I call conservative Bayes dynamics. Conservative because you don't give up your personality. You remain the same Bayesian agent. If a Bayesian agent is defined by respect to prior or background measure, then you remain the same, but you take into account feedback and you revise. So this is the revise and resubmit procedure. Okay? Quite painful. The other is the radical one. When you transform yourself at every step possibly into another Bayesian agent by discarding your background completely and adopting the background to which you have inferred in your first inference. Okay? So you infer something on the basis of some evidence, and then you trust it, or if you don't trust it, you disregard this, you dispose of your previous background, you adopt a new background, and you look for completely new evidences. So these are the two possible dynamics. There might be more, I'm not sure, but these are clearly two possible ones. And then the bit more precise definition of the conservative one is that this is a conservative Bayes learning path Q into Q prime if there is the same background, so the conditionalization is with respect to conditional expectations that have as a fixed parameter the background measure, but with respect to different sub-Boolean algebras, you conditionalize. Okay? That's a concept that defines a conservative Bayes learning path. And the radical one is when you have this series from Q to Q prime, what you do is what I just told you. Namely, you conditionalize with respect to this prior, this background, and with respect to a sub-Boolean algebra, which is A1. You infer this Q1, And then in the next step, you adopt this Q1 as your background, look for some new evidence, and you conditionalize. And you do this a finite number of times. What can we know about these two? Well, the first thing is the following proposition here, that the base accessibility relation is not transitive, which means that if you have this conservative path from Q to Q prime, this cannot be shortened to a single step. So, because this is not because this relation is not transitive. So, in other words, what you have here is that maybe you have been able to learn this Q prime from Q in a finite number of steps, by keeping your background and conditionalizing, using feedback and revision. But this step-by-step learning cannot be shortened by a single Bayesian learning route, so there is no role in conservative Bayesian learning. That's the way to put it. This is how I'm going to put it. Okay? How about the conservative one? It's coming up. But before doing that, I would like to point out the obvious, namely that the notions of weak base connectedness and base blind spot can be defined now with respect to these learning paths. And you can talk about conservative, respectively radical, weak base connectedness, and conservative and radical base blind spots. So, what are their features? Here's the first proposition. If this P state space is not weakly base connected, then it's not weakly base connected with respect to a conservative base learning path either. If you think of this for a second, then you will see immediately that this is trivial. This is obvious, but stated here for completeness. So if something is not weakly base connected, then it will not be base connected with respect to a conservative learning path connection. On the other hand, if S is a finite Boolean algebra in this, for this agent, then the P state space is weakly base connected with respect to a radical base learning path. I think this is what you might have had in mind when you were asking about steps. Well, this means that the baseline spot does not change when one switches from learning from single condition, when one switches from base learning based on a single conditioning to learning by a conservative base learning path, the baseline spot does not change. On the other hand, this means that the baseline spot disappears completely when you switch from learning by a single conditioning via you switch from learning by a single condition to learning by a radical based learning path, if S is finite. In fact, what can be proved is that this connectivity of the state space of finite Boolean algebras is weakly base connected with respect of learning paths of length 2. Very short, can be very short. There's a caveat here which I didn't put in, which is, I think, worth discussing if it comes up, but I'm suppressing it now. So what this means is that there is a role in radical base learning in the finite case, but I have no idea whether this is true if S is not finite. Doesn't seem to be obvious to me at all. And so it's not clear if there's a role of radical base learning in the infinite case as well. These are just open questions. Summary. So what I claim here that if you want to investigate and understand base learning based on the conditioning, then investigating those features based on the concept of conditional expectation somehow very nicely and very naturally reveals some very fundamental structural properties of Bayes learning, and in particular the existence of large baseline spots in typical probability theories. And you also see very clearly that there are two very different ways of Bayesian learning. If you move from one-step learning to that process of learning with respect to many steps, then you have the conservative ones, then you keep your background, and the radical ones, then you change your background. And then if you're a conservative Bayes learner, then the baseline spot, which is redefined with respect to the conservative learning path, does not shrink. And there's no conservative Bayesian roll learning. In the radical Bayes learning, on the other hand, the baseline spot, if it's redefined with respect to step-by-step connection, can disappear, not clear if it disappears all the time, or that it can disappear in every probability space. Sometimes it certainly disappears. And there seems to be Bayesian roll to learning, at least sometimes. It's not clear if it's always possible. I have not even conjecture about this, and there are a lot of open problems, as you have seen. These are the two preprints in which you can read about what I've talked about here in some more details, actually in much more details, because the proofs are detailed in these papers downloaded from the PIT archive. They're under review in